Hello, everybody. We will shortly get started on Unit 9-10 review. Let me close the blind. There's a lot of shadow. Okay, so I had over 30 kids tell me that they wanted this session, but I only see 4 right now logged in. Maybe they'll make their way over here or watch the video later. So I'm going to start by reviewing the concepts briefly and then answer your questions. So big idea 4 is chemical kinetics. And in chemical kinetics, we are interested in figuring out, first of all, what is the rate of reaction and what is the impact on the rate of the reaction of different things that you change. So one concept that we learned was rate. Rate of reaction, Rxn for reaction, is defined as change in concentration of, I'm going to use delta. So change in concentration of reactant with change in time, or change in concentration of product with change in time. And note that the units of rate are molarity per second or molarity per minute or hour, whatever the time units are, and molarity is moles per liter. Also know if I have a reaction A plus 2B gives you 3C. And I say rate of reaction of A is 2.5 molarity per second. What is rate of reaction of B? Or what is rate of reaction of C? Then using these coefficients, you can figure out the rate. So rate of reaction of A is minus 1/2 rate of reaction of B. So if you're asked rate of reaction of B, you multiply the rate of reaction of A by 2. If you are asked rate of reaction of C based upon A, then rate of reaction of C is rate of reaction of A will be 1/3 rate of reaction of C. So rate of reaction of C will be 3 times rate of reaction of A. So remember this relationship with the coefficients and the rates. The next thing that we were interested in this chapter is to figure out the effect of concentrations on the rate. And we were interested in figuring out the rate law. R is equal to K, A to the power X, B to the power of Y, where X and Y are the orders of reaction. Remember, orders are not correlated to the coefficients of a balanced reaction unless it is an elementary step. If it is an elementary step, then the coefficients represents the order of reaction, but if it is not an elementary step, if it is the overall reaction, then there is no correlation of order to the coefficient. The way you figure out order is through experimentation. What kind of experimentation? We call it initial rates method. And if they want you to use this method, the data that will be given to you will be generally in form of a table where you will be given concentration of one of the reactants, concentration of the other reactant, and the rate. And they would have different trials where they'll keep one reaction concentration constant and they'll double this and then see by what factor the rate changes. So you can figure out the rate law, basically the order, using this. Once you figure out the order using this, remember, you can also plug in another set of data to calculate rate in there, because K, rate constant, does not change with the concentration of reactants and products. Rate constant only changes with temperature. That is one method of figuring out rate law. This is called differential rate law method or initial rates method. There is another method of figuring out rate law that is called using integrated rate law. So there are three different equations. Concentration of A at T minus concentration of A at 0 is equal to negative KT. Our natural log of AT minus A, natural log of A0 is negative KT, or 1 over A0 minus 1 over AT minus 1 over A0 is equal to KT. These equations are given in your handout, in your equation sheet. And if you know if a reaction is first or second or third order, then you can use these equations to figure out either the time or the K. Remember one thing, guys, that the times unit and K's unit kind of cancel each other out. Sometimes they'll give you different units. Another thing about K's unit is they are not constant. They vary. You have to derive them every time. And the way we derive K's units is, think of a first order reaction as R is equal to K A. 1, we don't write ones. So K will be R over A. So rates unit are molarity per second, and this is molarity. So 1 over second or 1 over minute or 1 over hour. And if it is second order, then you'll do R squared. This whole thing gets squared. So it is 1 over molarity second. So you have to derive K's unit. They vary. So here we were talking about figuring out rate law using integrated rate law. And one way of applying integrated rate law is, if you already know what is the order of that reaction, then you can apply these equations. If you do not know what is the order of the reaction, you can still use integrated rate law in a graphical method. You plot a graph. You would have collected a bunch of concentration time data like you did in your CV lab. And if you plot concentration time data and you get a linear regression close to our squared value of 1, then you know this is 0 order. In this case, the slope of the line is equal to negative rate constant. If it is first order, then the linear regression will happen when you plot natural log of A against concentration. And in this case, this is first order reaction. And in this case, slope is equal to negative K. And if it is second order, then 1 over concentration against time will give you linear regression, but with a positive slope. Here, slope is equal to K. Note, any time, and let me write it in red. Any time is mentioned in a kinetics problem, that's your cue that they want you to use integrated rate law. So basically, the problem will guide you whether you want to go with the initial rates method or graphical method, or you want to use the equations. Going from here, let's talk a little bit about reaction mechanisms and activation energy. So if you increase the temperature, guys, then the rate constant, or decrease the temperature, then rate constant value changes. And remember that activation energy diagram where every reaction acts as if it has to overcome an energy barrier. And if these are the reactants, these are the products, this is the energy on y-axis, and this is the reaction profile as the reaction goes with time. This is the energy of reactants, and this is the energy of products. And as you can see, that products are at a higher energy. So now, knowing thermochem that you can say that this is a endothermic reaction. And the difference between product and reactant energy is called delta H of reaction. And the energy difference from the reactants to the barrier, or the energy that the reactants need to overcome the barrier, is called activation energy. Delta H reaction's numerical value is the same for forward and reverse reaction with the opposite sign. But activation energy does not have the same value for forward and reverse reaction. Activation energy for forward reaction is this much, but activation energy for the reverse reaction is just this much. Now I'm going to talk about reaction mechanisms. And because we cannot see inside a chemical reaction, we propose mechanism. And then we find evidence for that proposed mechanism by conducting experiments. What is true for all reaction mechanisms? Most of the reactions happen in multi-steps. And each of these steps is called elementary steps. No elementary step should be more than termolecular, meaning not more than 3 molecules must be asked to collide at the right, with the right orientation and correct energy, because the odds of that are very, very low. So elementary steps and this one. And every reaction has the slowest step is called slow step. And when you add all the elementary steps, it should give you overall reaction. And the slow step determines rate law. But one thing, remember guys, what you must remember is if there is, so one thing you need to remember, if an intermediate is present in slow step, then you must go to previous step and include its reactants. We've done problems like that. I did it more just to remind you of that fact. Okay, so one other thing I wanted to clarify, let's say if plus B gives you C plus D, and D makes E plus A. I'm just making it up. This is step 1 and this is step 2. So in this case, A is present at the beginning of our step and A is present at the end of second step. A is called catalyst because it is present before and after the reaction. That means it is not consumed in the reaction. D is intermediate because D is produced in the reaction and is consumed in the reaction. So this was Kinetics 101 for those 9 elements who are live with me. Do you have any questions on kinetics that I can further clarify for you before I move on to thermochem? So Brandon asked me if step 2 were the slow step. So I just made it up. It may not work, Brandon, but I'll try and work it with you. So if this were the slow step, then it'll be R is equal to K D, but we know D is an intermediate. So we'll need to substitute D with AB, but C is also produced. So really, to put it in terms of D, it is A over B times C. So R will be equal to K A B over, C. All right. Did you get it, Brandon? You're welcome. Anything else on kinetics? Okay, I assume there are no more questions. So I'm going to move on to thermochemistry. And in thermochemistry, there are many learning objectives, but pretty much in this chapter, our focus was on finding delta H of reaction, or standard enthalpy change of reaction, because we are interested in how much heat is released or absorbed during a chemical reaction, and we found different ways of doing it. One of the ways of calculating delta H reaction, guys, sometimes they'll give you an exothermic or an endothermic reaction, let's say Na plus dissolution of NaOH. NaOH solid plus water liquid gives you Na plus OH minus, and I'm going to make up some number, and they say delta H reaction is negative 15 kilojoules per mole. They may give it to you like this or in a more complicated equation, but generally they will give you 5 grams. They will ask you one or the other way. They may ask you 5 grams of NaOH was dissolved in water and it made negative 15 kilojoules per mole heat, per mole reaction heat, right? How much heat will be generated if 25 grams of NaOH were used? Or if they want to get trickier, what they do sometimes is they'll write an equation like that. Mg plus O to 2 MgO, and they'll write delta H zero reaction here as, say, negative 15 kilojoule per mole. And they will say, I mean, it's a big, long problem, but a part of that problem will say when, or they may not give this here. They may say when 5 grams of magnesium were reacted with excess oxygen, 15 kilojoule of heat was produced. And then they may ask you, what is the delta H reaction for the above reaction? Both of these problems are on the same concept. The concept is heat is an extensive property. You change the amount of substance producing heat, the amount of heat produced or released will be changed. So we know that 5 grams produce this much heat. And we know there are 2 moles of magnesium are reacting here. So we need to ultimately figure out 2 moles of magnesium will make how much heat. So either you can convert 5 grams to 2 moles, or you can figure out how many grams is 2 moles. 5 grams to moles. So it's basically keeping in mind the moment you change the amount of substance producing heat, amount of heat produced will be changed. So that is one way we calculated delta H reaction. Another way we learned to calculate delta H reaction was using this Big Mama equation, summation mole times heat of formation of products minus summation mole times heat of formation of reactants. So heat of reaction is different from heat of formation. So if we have Fe2O3 plus H2 gives you Fe plus H2O. I don't know if it's even feasible. Let's try it. 6, 3, 4. Yeah. Okay. So let's say I gave you this equation and I said delta H, I'm making up all of these values, guys. I don't remember any of these values. So let's say delta H reaction is negative 15 kilojoules per mole again. This per mole is per mole reaction. It's not for a specific reactant or product, but moles overall. Remember, this delta H reaction is for this entire reaction when multiple compounds are reacting. Heat of formation is for individual compounds. Fe2O3 will have a heat of formation. H2 will have a heat of formation, but in gaseous state, it will be 0 because pure elements in their natural state have 0 heat of formation. Fe's heat of formation will be 0, and this will need to know liquid or gas because heat of formation is different. So in this case, if we wanted to use heat of formation data to calculate heat of reaction, it will be 6 times heat of formation minus of water liquid minus 2 times heat of formation of Fe2O3. That will give us heat of reaction. So please distinguish between heat of reaction and heat of formation. The third type of problems here were, we did the calorimetry problem where we used delta H reaction. Oh, sorry, we did Q reaction and then converted to delta H in your lab, hand warmer lab. Q reaction plus Q calorimeter plus Q solution is 0. Q solution is what we're trying to figure out. Q reaction was MC delta T. Remember, if you're talking about dissolving a solid, this mass is of solution, not solute or solvent, but solution. Okay, and Q calorimeter is C times delta T. Please pay a lot of attention to the units. I saw when we did practice problems, you guys, Q is often given in kilojoules and specific heat is generally given in joules per gram degrees Celsius. So please do not confuse between that. Make sure your units are same or aligned. And then you figure this out. And delta H and Q are different from each other. If you divide Q per mole, that becomes delta H. That is the difference between them. Then there is Hess's law. But before I go there, what else do I want to remind you about this? Another problem that so I'm going to take this problem because somebody yesterday was asking me this and I thought I'll address that. I don't know which problem it was, but I'm going to make up something similar to that. So if I say 2 molar 20 mil HCl reacts with 2 molar 20 mils of NaOH, what is the enthalpy of neutralization in this reaction if the density of solution is 1 gram per ml and consider the specific heat of the solution, lowercase c, to be 4.18 joules per gram degrees Celsius. Now, heat of neutralization, guys, is how much delta H0 is there per mole of water formed. That is its technical definition. Like heat of formation is 1 mole of a substance formed. Heat of combustion is 1 mole of a substance combined. Heat of neutralization is 1 mole of water formed. So when you have, so you need to figure out how many moles of water do you have here, HCl do you have here. So 2 times 0.02, 0.04 moles, right? And you have 0.04 moles of this, and you know when 0.04 moles of the acid will react with 0.04 moles of base, because NaOH plus HCl is NaCl plus H2O. If you take 0.04 moles of each of these, you'll make 0.04 moles of water. And I say that how much is heat of neutral? So I'll need to tell you how much is the heat, the temperature rises from 15 to 25 degrees Celsius, right? Let's say I said that as well. So Q is mc delta T. Now this mass, guys, our strategy is first we figure out Q, then we divide it by moles to get delta H. This mass will be this solution and this solution. You use the volume of the solution to get and multiply it by density. So density is mass over volume. So mass is density times volume. So you take this volume, multiply by the density. So it will be 20 grams. And then this one will be 20 grams. So your mass here is 40 grams. And specific heat is 4.18 joules per gram degrees Celsius. And delta T will be 25 minus 15, right? And whatever you get, let's say X joules, you divide it by 0.04 moles, and then you get answer delta H in joules per mole. A commonly made mistake, guys, is this. Kids multiply 2 by 20 or 2 by 0.020 molarity times volume. They get 0.04 moles, and then they use the molar mass of HCl to convert it to grams. No. Why not? Let's look at it. You have a solution. You have 20 mils of 2 molar, right? So how many moles? You have, let's say this is HCl, right? It will be dissociated, right? It's a strong acid. So H plus Cl minus, H plus Cl minus. I'm drawing 4 because each one is representing 0.01. If you take the moles of HCl, when you multiply molarity by volume, it is only solute, not solvent, right? There is HCl in here and there is H2O in here. If you take only HCl and multiply it by molar mass, you will only get mass of HCl. That's erroneous. You can't do that. So in these kind of problems, you must use the volume of the solution with density to figure out what is the mass of the solution. So that was one thing that I noticed I thought I should address. Last thing in thermochem is Hess's law. And Hess's law pretty much is manipulating equations to get your desired equation. And I don't know if I need to go any deeper in that. But one thing that kids ask me, will they give you more equations than needed for Hess's law? Well, depends. Sometimes they may give you more equations, generally not. Sometimes they give you equations. Sometimes they'll also have you write equations. So that pretty much is a summary of kinetics, and thermochem has the common misconceptions or commonly made mistakes. It is not comprehensive by any means, and I have no handouts with me. I didn't come very prepared to do this today. I thought it was Super Bowl Sunday and everybody will be busy partying. So I'm just going off of my memory. If there is anything else that I can address concept-wise, please chat me. I will take those. Shravya, in that problem that we did before that, you multiply 2 molarity by the volume to get how many moles of HCl so that you can see how many moles of water you will form. Because enthalpy of neutralization is defined as per mole of water formed. So you need to know how many moles of water are being formed. And remember your titrations chapter way back in first semester. You have to write the equation to see how many moles of acid you have, how many moles of base you have. They're 1-to-1 ratio. Then you form that many moles of water. There could be limiting reactant or a different mole ratio as well. So that is the significance of molarity. Yes, Bhavik, I can take problems, but I have no handouts with me. So either you can type the problem, or if you are going to ask from practice test, then I can pull up practice test. So let me know where you're asking the problems from so I can pull it up. I'm ready for your problems, guys, whether from the problem set or from the practice. You're welcome, Shravya. Number 4 from practice. Let me pull up. Is my practice test linked to online? I don't think so, right? Let me go to my drive. Hey guys, I have a question for you. Can you still see me? Do you see my screen or no? When I go this way, because I'm now in my drive. What do you see right now? Oh, you can see me, so you don't see my screen. Okay, all right. So thermocam. Okay, Bhavik, which problem you had asked about? Number 4, free response. Ethene may be prepared by dehydration of ethanol, molar mass this much. Setup is shown, and delta H for this. A student added, I'm doing number 4. .2 gram sample of C2H5OH. To a test tube. The student heated the test tube once it evaporated. Heat. So in this problem, they say when you make 1 mole of ethene, it is C2H5OH liquid gives you C2H4 gas plus H2O gas, I think. Yeah, and it's negative 45.5 kilojoules per mole. So with this amount, you make how many moles of ethylene you're using here? You are using 1 mole, right? Or you're producing 1 mole. So if you use 0.200 gram, you convert, use the molar mass of C2H4 is 1 mole, right? So you know how many moles is that, and then using the ratio. When 1 mole of ethylene C2H4 is produced, you make negative 45.5 kilojoules per mole. And when these many moles are produced, how many moles of heat will be produced? So this is an example where you use the extensive property of heat produced based upon the amount. Did you get it, Bhavik? Oh, I think I changed this problem on your test. Did I or did I not? Is that the answer, guys? So you get the moles and then you find, I think it is the heat, and I recall it is 0.197 kilojoules per mole. Was that right? Okay, thank you. Thank you, Shravya and Karina and Pranav. Okay, now 1B from practice test. And Shanali, I'm assuming that is free response, right? 2A and 2B, 1B, 2A, 2B. So 1B. 1B. When oxygen is not available, glucose can be oxidized by fermentation in the process. So in one B. So in 1B, you have C6H12O6 solid gives you 2 C2H5OH liquid plus 2 CO gas, and it is negative 68 kilojoules. And they say when oxygen is not available, it uses another reaction, which is, oh, this is CO2. And the other reaction that is given to you is C6H12O6 plus 6O2 gives you 6 CO2 gas plus 6 H2O liquid. And you calculated delta H for this reaction in part A, right? You already know delta H0 of this from part A. Now they ask, using the answer, calculate delta H0. So your desired equation is C2H5OH plus 3O2 gives you 2CO2 plus 3H2O. So if you want this equation out of these two, because you know delta H for both of those, what you can do is keep the second equation as such, because you want C2H5OH on the reactant side. So you flip this equation, and when you flip it, what do you get? You get 2C2H5OH plus 2CO2 gives you C6H12O6. And when you flip it, the sign gets flipped, so it's plus 68 kilojoules. And the second one stays the same, C6H12O6 plus 6O2 gives 6 CO2 plus 6 H2O, and whatever the value you got from part A. And when we do that, then C6H12O6 cancel out, 2 CO2 with 6 is 4, and that's it. So let's copy it over. 2C2H5OH plus 6O2 gives 4 CO2 plus 6 H2O, and then you will add these algebraically and you'll get a value here. But this is exactly double than what you need. So you divide this whole equation and this value by half, and then you get your desired equation. So this is using these two equations to come up, using Hess's law to come up the answer for your desired value. Did you get it, Shonali? Okay. And then Shravya wanted 2A and 2B. And the 2A says calculate the amount of heat needed to purify 1 mole of aluminum, originally at 298 by melting it. The melting point is at 933 Kelvin. And molar heat capacity is lowercase c, which is 24 joules per mole Kelvin. Remember, molar heat capacity, this is molar. Generally, we use specific heat capacity or specific heat, that is in joules per gram Kelvin. But when instead of gram we use mole, rather than calling it a specific heat, we call it molar specific heat, because now we are talking per mole of a substance. And heat of fusion, delta H0 fusion of this is 10.7 kilojoules per mole. So guys, here, the thing is to melt 1 mole of aluminum, which is at room temperature, right? Or environmental temperature. This 1 mole of aluminum is at 298 Kelvin. First, we'll need to heat it to make it 933 Kelvin aluminum solid, right? Increase its temperature. Only then, when we further heat it, this 933 Kelvin aluminum will melt into liquid. And the Q here will be calculated using MC delta T, and Q here will be calculated as mole times delta H of fusion. So let's calculate it. Q MC delta T. We have 1 mole. Specific heat or molar heat is 24 joules per mole Kelvin, and we rose temperature to 933 from 298 Kelvin. Oh God. Okay. And when you do it, you'll get some answer. Oh goodness, my kids, just a second. Hun, can you tell Linda I can talk right now? Okay. And then you get MC delta T. And then you take, so this is for this step, right? And then for the next step, Q is mole times delta H fusion. Let's do that. And we have 1 mole here, and delta H fusion now we know is 10.7 kilojoules. And this is where they get you, because this answer is in joules and this is in kilojoules. So you need to convert this kilojoules to joules, add both of them up, and that should be your Q. So that is part A. And part B of this is the equation for overall process for extracting aluminum. So one way of extracting aluminum is by recycling, right? You use aluminum foil for wrapping your sandwiches, and then you crush it and you put it in recycling. So when it goes to these recycling centers, they melt it to be reused, right? So this is the process they use. Now, another way you can make aluminum is from aluminum oxide. Trying to see where's room over there. Okay, so aluminum oxide, Al2O3, it is called bauxite. It's a ore of aluminum. You can mine it from the ground, and then you purify it, and it gives you 2 aluminum solid plus 3/2 O2, and delta H is -1675 kilojoules per mole RxN. Okay? So if you look at this value, how many moles of aluminum are you making here? This amount is for mole of reaction when 2 moles of aluminum are produced. So for 1 mole, it will be half of this, negative 837 something, right? Kilojoules per mole aluminum. Remember, they are testing the same concept. In all the problems you've asked me, they are testing the extensive property nature of heat. When you change amount of substance, the amount of heat produced is changed. And then you compare heat here to the recycling, and you'll realize that recycling or melting aluminum requires much less energy than to make it from its ore. I'm going to put the screen down a little bit. Alrighty, guys. So those were the problems that you asked for. Are there any other problems? So who else is excited for the halftime show? Maroon 5, guys. Yay. Already, I'm assuming there are no more questions, guys. So you had me, Shravya, you had me do all of these for nothing? Are you sure you want me to do 3B? Okay, I'll do 3B. So 3B says calculate the magnitude of heat absorbed by solution during dissolution process. Assume. So in part A, you have done in 3A, you calculated Q of reaction, right? MC delta T. When you did Q of reaction, you know that Q comes from 10 grams of lithium chloride because the student is dissolving lithium chloride in water, okay? So if a student is dissolving lithium chloride in water, lithium chloride is the one making heat, right? Water is not making heat. So you know that 10 gram of lithium chloride makes whatever amount of Q in joules or kilojoules you got in part A. To calculate delta H of reaction in joules or kilojoules per mole, you have to convert 10 grams of lithium chloride to moles of lithium chloride by dividing by its molar mass. And then if you divide this heat by moles, then you will get heat enthalpy change in joules per mole. Just like you did in your hand warmer lab. You first calculated Q of solution, and then you divided it by the moles that were in 5 grams of your salt to convert it to delta H. No problem, Savya. Got it? You're welcome. Okay, guys, unless there are more questions, I think I'm going to call it a day. Go watch some Super Bowl. Okay, Elements, thank you for being with me, and I'm going to end the stream. I'll post this video on Facebook group. Bye, guys.